This lesson will be a general introduction to O1 to get you familiar with how it's so different, how it functions, and what people are using it for. Before O1, you could think of most models as like children. They always say the first thing that comes to mind. As they grow up, they need to be taught a valuable lesson, that they should think before they speak. What makes O1 so different is that it explicitly thinks before it speaks every time. This helps it reach new levels of performance at complex tasks in domains like math, coding, science, strategy, and logistics. The way it does it is by using chain of thought to explore all possible paths and to verify its answers as it produces them. This means that O1 requires less context and prompting in order to produce very effective results. We've released our first two models in the OpenAI O1 series. The first is O1, our mainline reasoning model for complex tasks that require broad general knowledge, which includes function calling and image input. We also have a faster, more cost-efficient version called O1 Mini, which is tailored for coding, math, and science, and designed for those more cost or latency sensitive use cases. The thing that makes the O1 family of models so different is how they natively integrate chain of thought into how they solve problems. Let's take an example where we give these scrambled letters and we translate them for the model, and then we give it a new problem to solve. The way it solves it is something like this, where it thinks through what it's given and talks itself through how to solve the problem. It recognizes the example and then understands the transformation that took place here. Then it comes up with hypotheses and tests them. For example, it thinks maybe there's an anagram or cipher here. Then it notices that the ciphertext words are exactly twice as long, so maybe then comes up with an idea to test. It tests it and finds that it doesn't work, but uses that to iterate to a new hypothesis, which gets it to the right place. And this, in a nutshell, is what makes O1 so special. Rather than you having to prompt it to do this, we've trained the model to natively apply this reasoning process so that it can work through more complex problems in many disparate domains like science, law, coding, and math. This introduces a trade-off when you're using the O1 family of models, where you generate extra completion tokens, which you don't actually see, but which the model is using to problem solve your task. Let's look at how it works. We can see here that completion tokens can be broken into two distinct categories. We can see our gray reasoning tokens here, and the actual output tokens, which are the tokens which you are provided for your generation. It's important to note that reasoning tokens are not passed from one turn to the next. If you want to do something like this, you'll need to prompt the model to output some kind of reasoning which you can choose to pass from one turn to the next. What this means is you also need to consider those reasoning tokens in the cost of what you're paying for, and also when you're calculating your context limit, because those reasoning tokens do count towards the context limit, and if your output goes over and above that, the output will be truncated. Two of the key breakthroughs that led to O1's increase in performance were, first of all, recognizing that during the post-training process, the more reinforcement learning we did, the more accurate the model got. But what was possibly more surprising was the more we allowed it to think at inference time, we got an even sharper increase in performance. So the key breakthrough here was the ability to think for a longer time at inference time and get better results. The other key breakthrough that led to the increase in performance with O1 was teaching it to verify outputs via consensus voting. The way this works is that we generate a bunch of solutions and train the LLM to choose the most common one. You can think of this as similar to when we sample at low temperature. In one paper, we saw a math benchmark go from 33% to 50% improvement purely due to consensus voting. Consensus also flatlines before 100 samples, so you don't need a huge amount of samples to realize the performance improvement here. So what's the significance of all these breakthroughs? The results of O1 have so far been really good. For example, here's one benchmark that shows the difference between GPT-4o at 13% on this benchmark and the new O1 model, which got up to 83%, a huge improvement. Similarly at code, where GPT-4o scores 11% and we see O1 at 89%. And science, where we don't see as big of an improvement, but still 20-odd percentage point improvement on this benchmark. This carries on to other families of benchmarks. For example, math, where we see a giant 30% improvement from O1 over 4.0. Science, 20 to 30-odd% improvements. A variety of different exams, most impressive one here being the LSAT at almost 30% improvement. And lastly, the MMLU categories, where there was improvement across the board, with the highest scoring being a 98.1% on college mathematics. Just super impressive and a massive improvement over the previous family of GPT-4o models. So how does the O1 model actually work? The key factor is that it uses large-scale reinforcement learning to generate a chain of thought before answering. This chain of thought it produces is longer and higher quality than what you can typically attain via prompting alone. It also contains behavior like error correction or trying multiple strategies and selecting the best one, or naturally breaking down problems into smaller steps. There's a bunch of examples of these chain of thoughts on the research blog post if you want to dig a little bit further. One other area that O1 represents a new standard of performance over the 4.0 models is abstract reasoning. I'll give you one challenge here. We gave GPT-4o 16 words, and it was challenged to identify the 4 categories which united those words, and then place the right terms in each category. And you can see here that its performance was fairly haphazard. So other than approval, it was only able to identify one other category, which is movement/action, and it misidentified one of the terms. Whereas when we tried it with O1, it was able to correctly identify both the 4 categories and all 16 of the words. The reason we're so excited about this kind of abstract reasoning is it doesn't easily fit into the same bucket as coding, math, or any of the other benchmarks that we've shown, but it shows some of the other emergent capabilities that the O1 model is starting to show. And we're very excited to see you all test it with your own use cases to figure out where else these kind of abstract problem-solving capabilities are going to be significant. The last area we want to highlight where we've seen significant emergent capability from the O1 family of models is where we have a generator-verifier gap. What we mean by that is, for some problems, verifying a good solution is easier than generating the perfect solution up front. For example, with Sudoku, with math, with programming, you can often generate a half-decent solution, verify it, identify the issues, and then use that to iterate to the next one much more easily than building the perfect solution up front. There are also examples where this verification generation approach doesn't work. For example, for information retrieval, where the question does need to be answered correctly the first time, or with image recognition, where you need to correctly identify what's in the image first time. But where a generator verifier gap exists and we have a good verifier that can run the verification process, we can continue spending more compute at inference time to achieve better performance. And for these, we're seeing O1 demonstrate great capabilities. So where might the O1 models actually be used? In areas like data analysis, interpreting complex data sets like genome sequences, or mathematical problem solving. We've seen a ton of benchmarks here, but this is an area where we really see a step change in performance versus the previous family of models. Similarly, experimental design, so coming up with innovative approaches for niche domains like chemistry or physics, is another area we've seen pretty encouraging results. Scientific coding as well. You'll notice a common theme here, a lot of STEM subjects, a lot of math, a lot of coding that we're seeing great use cases for O1. Biological, chemical reasoning is another one, and algorithm development. Literature synthesis is the last one that I want to highlight here, where reasoning across multiple research papers to form coherent conclusions or summaries is another area where we're seeing great capabilities from O1. So let's recap the key takeaways from this introduction to O1. The first is that the O1 family of models scales compute at inference time by producing tokens to reason through the problem iteratively. O1 gives you more intelligence as a trade-off against higher latency and cost, so it's not appropriate for all use cases. It can also perform really well at tasks that require a test and learn approach, where it can iteratively verify its results. Some of the great emerging use cases we're seeing are planning, coding, or domain-specific reasoning in fields like law or STEM subjects. So let's jump into some of the practical applications that we're seeing and walk you through how you can make use of O1 for your use cases. I'm going to show you a quick example of how O1 works within chat completion. First, I'll import my API key and set up my OpenAI client. I'm going to set O1 mini to be the O1 model that I'm going to use. And I'll queue up a chat completion request. You can see O1 requests are exactly the same as your typical chat completion request. We specify an O1 model, and I'm going to give it the classic question, how many R's are in strawberry? We'll generate this, see what comes back. Let's have a look at the response object. We can see here the standard chat completion response. We've got a chat completion message in here. We have the output. The word strawberry contains 3 letters and a couple of other outputs. Now, the thing I want to focus on here is what makes O1 different. Here you can print out the tokens. We're going to focus on the prompt tokens, the total completion tokens, and then the constituent parts of the completion tokens, which consists of the reasoning tokens and the output tokens. If we print these out, you'll see that the model did a ton of thinking here. So we gave it only 15 prompt tokens, but it produced over 1,000 reasoning tokens to reach the output. This highlights the key trade-off with O1. You're getting much greater intelligence, but in this case, we paid a 10x premium in terms of the amount of output tokens that we paid for to get this. This is a key thing to consider. You don't use O1 for everything. It's only for those use cases where the increase in intelligence you get is worth the trade-off in latency and cost. This lesson will cover 4 key principles we've worked out during the first months of using O1 models. These aren't exhaustive, but they should give a great starting point for you to explore the differences between our other models and this new family of reasoning models. We're interested in hearing what principles work best for you. All right, let's take a look. There are 4 principles for prompting the O1 models. The first is to be simple and direct. Try to write prompts which are straightforward and concise. You'll find that direct instructions yield the best results with these models. The second is that no explicit chain of thought is required, and this may be somewhat different from what you're used to with LLMs. You can fully skip the chain of thought reasoning prompts that you used to provide, like think step by step and things like this. The O1 models are trained to infer and execute these itself without providing your own breakdown. The third is to use structure. So try and break complex prompts into sections using delimiters like Markdown or XML tags. The structured format will enhance model accuracy and also simplifies your own troubleshooting. We'll see a couple examples of that here. And the fourth is to show rather than tell. This comes back to our first principle. Rather than giving a lot of prompt to tell the model how to act, it's often better to give it 1 or 2 contextual examples to give it understanding of the domain of your task. Let's jump across to the code and see how these work in practice. You'll start off by importing your OpenAI API key and the variables that you'll need to run these. You'll notice here that we've initiated the OpenAI client with our API key, and we've also imported a GPT model and an O1 model. For the purposes of these lectures, we've used the GPT-4o mini model as our kind of base model to compare against. And for the O1 model, we've used O1 mini. Both of these are for reasons of cost and latency. These are faster, cheaper models. We'll start with the first 2 principles, which are being simple and direct, and that no explicit chain of thought is required. I'll start with an example which breaks these rules. Looking at this prompt that I've pasted in here, we're instructing the model to generate a function that outputs the SMILES IDs for the molecules involved in insulin. Then we moved on to give it some chain of thought instruction. So we've asked it to think step by step, and we've given it 3 steps to work through. And we've also given it a start-in prompt to kind of give it a hint as to how we want it to start. Now, with O1 models, we've trained it to act and reason in the way that we think is optimal to solve these sorts of problems. So we're going to see in a second why it's better to just give a simple prompt without these. But let's run this first to see how the model behaves with this explicit chain of thought prompt. We're going to display the results here. You'll notice I've given a couple of HTML headers because the model's outputs can be pretty verbose. So we've tried to signpost where the content starts and ends. Having a look at this, we can see the model's output. So The first thing is that it has followed our instructions, but it's followed them explicitly. So it's given us a large number of preceding steps before actually going and solving our problem. This is one of the consequences of adding explicit chain of thought. The model will often explain itself a couple of different times, and you may end up with an overly verbose output. You can see here that it finally creates the function in step 3. Again, it's reprinting the smiles codes, the amino acids that it's going to process for this task, and then it gives us a sample output. Then at the end, it summarizes the explanation and reasoning that it used to come to this and gives us a conclusion. So it did answer our question, but it gave us a lot of extra information, which is probably not needed for getting the output that we're looking for. So let's change the prompt, apply our principles, and see how the output differs. This next prompt applies our 2 principles. You'll see here that it's simple and direct, telling the model to generate a function that outputs the smiles IDs for all the molecules involved in insulin, and contains no explicit chain of thought prompting. You'll run this and get some results. Here we have the same formatting that we had above, and here you'll see a quick description of the task. It describes what insulin is, how it's going to get the smiles codes, and then jumps directly into the code. So a much more efficient response this time. We've got our full Python function here, which we can run, and an example of it being used. It then provides a little bit of explanation at the end as to the assumptions it's made, and a sample output of what it thinks is going to come out the other end. It also supplied an alternative approach, and finally, a conclusion. So the point here is it didn't require that explicit chain of thought prompting. We've trained the model to provide what we think is an effective level of explanation with its responses, and that is always a good place to start. That is not to say that you won't need to add your own chain of thought prompting for specific or very nuanced tasks, but it's always best to start from a baseline of being simple and direct with no explicit chain of thought prompting. Let's move on to the next principle. Feel free to pause here and do your own analysis using these principles. You might want to look for the molecules involved in ibuprofen or aspirin or other common compounds. The key thing is to try breaking those rules, so giving it a verbose prompt or providing chain of thought prompting, and then looking at the impact it has when you simplify and trust the model to do its own chain of thought prompting. The next principle is to use structure when prompting O1. In this case, I've got a lengthy prompt here where I'm prompting the model to act as a customer service assistant. You'll see here that I've used XML tags to give structure to the prompt. So at the top, we have a set of instructions, and in those instructions, we told it to follow your policy. We've then used structured formatting to provide it a policy tag, so that it's very clear to the model what we're referring to when we say the policy. And then within this policy, we have a series of different criteria. So what it's allowed to do, how it handles refunds, and compliance, so which policies it should adhere to. We're then providing a user input at the bottom, where we have a user query tag, and within that we have what the user is explicitly asking for. I'm going to run that and print the prompt so that we can see it in full. There we are, our instructions, a policy, and then we will add the user input on the bottom. Here we have our request, so we're using the O1 model, and the content is going to be the structured prompt with the user input appended on the bottom. Let's run that and see what the result is. We'll print the results to see how the model's responded. It looks like it successfully followed the process. So we said that a product didn't meet our expectations, and it matched that to the return process successfully. Let's give it one more test to see whether it maintains performance if we ask it about one of the other policy areas. Here's another user query. You can see here we've asked it to write me a haiku. So in this case, we're breaking the policy. We're asking for something that the model shouldn't comment on. If you run this, you'll see how the model responds. Here's the same request as before. This time, we'll take our structured prompt, add our refusal question, or the question we're expecting to be refused. And let's see what the output is. Great. It's adhered to its policy again, in this case, refusing this question, because this violates its policy rules. So we've seen how providing a structured input prompt to O1 models can ensure that they'll follow the instructions with greater accuracy. We've combined that with being simple and direct, and we haven't given any explicit chain of thought prompting, so we're starting to build up some good principles. I'll move on to the final principle. The fourth and final principle is to show rather than tell. You'll see here a prompt where we're asking the model to pretend to be a lawyer specializing in competition law. So again, we've given a prompt structure at the top and a policy is, again, telling it to maintain clear and accurate information about competition law and also to avoid giving specific legal advice without sufficient context. There's a simulated user query here. So a customer asking that a larger company is offering suppliers incentives not to do business with them and asking if this is legal. Going back to the principle here, at this stage we have not shown rather than told. We've just given it instructions and we haven't specified how we want it to act. If we run this, we'll see how it performs out of the box. Got another request here, our base prompt with the query appended to the bottom. Here we'll examine the results. You can see the model has acknowledged the question of the user and then provided a write-up. Great, but in the case of legal answers, I actually want the model to use specific references to evidence the position that it's taken. I could tell it to do this explicitly by adding more prompt, but instead I'm going to provide it an example input and output along with my prompt and trust that the model will learn from the style of what I've shown it. Again, I don't have to explicitly tell it. I'm going to show it by giving it an input-output example as well as the prompt. Here's our updated prompt, which adheres to the principle of showing rather than telling. You'll see the same two structured elements. We've got a prompt and a policy, but after those, I've included an example tag, and within that, I've got an example question and an example response. If I scroll across here, you'll see that I gave specific examples, and then I also referenced the relevant acts which cover the legal recommendations that I've given. You can see that I've done this in each one of the points that the model has supplied. What I'm hoping by doing this is that the model will learn that I want a series of bulleted reasons for my question, and wherever possible, that I want it to reference itself. So let's run another example question and see how the model responds and see whether it manages to reliably follow what it's seen here. You're going to run this new prompt with the example included with the same legal query as we had the first time. We'll now submit our updated prompt with the same query from the first question. Time to display the results. You can see here again a preamble and then our bulleted reasons. And great, it looks like it's successfully learned that it should reference itself. So we can see an example here. We can also see an example here and an example here. Now, it's given me a couple of examples, but it hasn't referenced every one of these bullet points. So this is telling me I might want to give it maybe 2 or 3 examples so that it can learn even further by showing. You can always add prompt, but as a general principle, it is better with O1 to give it the examples and let it figure out the reasoning that it needs to do to get consistent